Welcome to the Pre-Calculus Mathematics for Calculus textbook series. This lesson is written based on Chapter 3, Section 3, Part C, the remainder and factor theorem. Today, we're going to learn more about we're going to use synthetic division in the remainder and the factor theorem. So you should already know how to divide polynomials using synthetic division. We won't learn any new words, so let's just jump in. For our warm-up, I need you to evaluate a couple of functions. Pretty easy. Pause and restart when you're ready. I'll start in 3, 2, 1. Okay, how did it go? Okay, now this is an essential skill for what we're going to do today, so make sure to brush up on it before we get started. Synthetic division is a huge plus for finding roots of polynomials manually. But we can also use it to evaluate polynomials using the remainder theorem, which states that if a polynomial p of x is divided by x minus c, then the remainder is the value p of x at x equals c. In short, the remainder is the value of the function. For our first example, we're given a polynomial, and we need to find the quotient and the remainder when it's divided by 2, x plus 2, sorry. So that's simple using synthetic division. Once we complete our division, we can see that the quotient is 3x to the fourth minus x cubed minus 2x squared plus 4x minus 1, and the remainder is 5. Now we need to use the remainder theorem to evaluate the function at p of negative 2. Now that's done pretty much already because the remainder theorem tells us that when our polynomial is divided by x minus negative 2, which is x plus 2, the remainder is the value when x equals negative 2. Zeros and factors have a relationship, and as a result, we can apply the following theorem. The factor theorem states that c is a zero of p of x if and only if x minus c is a factor of p of x. Now let's think critically about what that means. The following three statements are equivalent. If x equals c is a zero of the function, p, then x equals c is a solution to the polynomial equation p of x equals 0. And x minus c is a factor of polynomial p. If one of these statements is true, then all of the statements are true. That's what the factor theorem is in a nutshell. So we have a polynomial, p of x equals x to the third minus 7x plus 6. And we need to show, first of all, that p of 1 is equal to 0. And then we're going to use that fact to factor p of x completely. So first, to show that p of 1 is 0, all we have to do is substitute 1 in for our x's. Okay, done. Now, our next step is to perform either synthetic division or long division to get the quotient, which is going to be another factor. You can choose which method you prefer, but in this case, synthetic division is probably faster. And don't forget your placeholder for the x squared term. So now we can use the information that we just learned to completely factor p of x. Think about it. We started off with p of x, which was x cubed minus 7x plus 6. Then we did synthetic or long division to factor that into x minus 1 times x squared plus x minus 6. Now we can just use plain old factoring to split x squared plus x minus 6 into x plus 3 times x minus 2. Example 2. Find a polynomial of degree 4 that has zeros -3, 0, 1, and 5, and the coefficient x cubed is -6. So it's a fourth degree polynomial, so we can start by setting up 4 factors. The factor theorem tells us that if we subtract each 0 from x, then we have our factors. So I'll simplify and then expand. Now I have a polynomial with the right factors, but my coefficient of x cubed is supposed to be -6. If I multiply the entire polynomial by the same number, it doesn't change my factors. So I'll multiply by 2 to get q of x equals 2x to the fourth minus 6x cubed minus 26x squared plus 30x. Great job today. It's good to see all of that long division practice pay off. Before you go, determine if the following statement is true or false. Zeros and factors of polynomial equations do not have to be related.